Okay, now that we know how to use derivatives to find different rates of change in an object, which is a big part of this unit, we're now going to explore error. Now, error is basically when a measurement is not taken super specifically. So, for example, let's say someone said, ideally we want this stick to be 5 meters long, but if it's half a meter bigger or smaller, it's no big deal. We want it to be between like 4.5 and 5.5 meters. Then you could say that the length of the stick was 5 meters plus or minus 1/2. And by saying this, you're saying that this basically is saying all the values that it can be. It can be 5, and it can be within 5 minus 1/2, which is 4.5, and 5 plus 1/2, which is 5.5. So that's basically like saying it would be acceptable if it was 4.5 to 5.5. So a plus or minus 1/2, no big deal. And looking at this, this right here would be the length of the stick, and this right here would be the error in the length of the stick. Now, error doesn't always mean a bad thing. Like when you say, oh, you had so many errors on your test, that means you did a lot of things wrong. But in this case, error simply means how much something is off by. And in mathematical sense, it's actually not the worst thing in the world. So I'm going to go ahead and do a problem showing you what you're going to be doing with error. Now that we know how to use the rate of change of one part of an object to find the rate of change in another part of an object, we can use this to say, if we know the error in one part of an object, let's find the error in another part of the object. So I have a story problem right here that I'm just going to use because I know the numbers work out nice. I'm going to type the problem into the description, but I'm going to read it right now. A manufacturer of manhole covers, pothole covers in the street, needs them to have a radius of 8 plus or minus 1/2 inches, meaning that ideally we want it to be 8 inches, but if it's 1/2 of an inch more, 1/2 of an inch less, it's no big deal. Find the related error in the calculation of the area using differentials. So basically, if the radius can be off by 1/2, then how much would that make the area off? Is basically what we're looking for. So let's define our variables. We know that ideally we want the radius of the manhole cover to be 8 inches, right? Inches. And so when you define what R actually is, that's like the middle point. That's not including error. That's like ideally what you want it to be. Now, in a calculus sense, we're going to call the error dr. And you can go back to the graph that I showed you, and I believe the second video from this unit, to see why, because we're doing kind of like an approximation kind of thing. But dr is going to be the error in the radius. And so that would be plus or minus 1/2. Yes, you do need the plus or minus. And we're looking for what is the error in area, so we'd be looking for dA. Put a big question mark, because we don't know what it is. Well, once again, we need an equation that's going to relate all of them. And because these are circular manhole covers, we want to know area of the circle in respect to the radius. So once again, we're going to use area equals pi r squared. Now, in this case, there's no time, so we don't need to take this in terms of time. We're going to go ahead and take it in terms of radius. Why? Because we want to have a dr in here somewhere. You could take this in terms of area, and you would end up getting dA over dA, which would just equal 1. And then you have to take this r and then add a dr dA, because of the chain rule. So you could take this all, let me write it here. You could take it dr or dA. You'd get the same answer, but one of them's going to be a little more impractical, and I feel like in this situation it's easier to just do dr. But if you did it the other way, doing dA, then remember a you would treat like x, you could just make that 1, and then this would be 2 pi r times dr dA. Either way, you're going to get the same thing. It's, in some situations it's going to be a little messier to do one over the other. I'm going to do dr for this example. You can do dA. So we would take the derivative of this, which would be 1 times dA dr equals 2 pi r. And because we're taking it in respect to r, we don't have to have a dr because dr is 1, because you're dividing the same thing over itself. Yeah, did you know that like dAdr, you're actually dividing the area of the area divided by the area of the radius. It's a little hard to picture that. So my point is you can actually separate this. That's going to be very important in a later unit. But we are looking for certain values, so we're going to have to separate this. So let's do it. dA equals, and multiply the dr to the other side. You get 2 pi r dr. And now it's just a matter of plugging numbers in. 2 pi, and the radius is the ideal one, which is 8. And the dr is the plus or minus 1/2. Make sure to keep the plus or minus in. So now, when we're solving for dA, you're going to get 16 times 1/2. So it will be 8 pi plus or minus. And that's why you keep the plus or minus in, because think about it. If you took it minus 1/2 inches, then you would actually get minus 8 pi. And if you took it plus 1/2 inches, you would get plus 8 pi. So you need to keep that plus or minus in there, unless the problem says specifically you're going to be going up instead of down or something, which probably will not happen. And this would be inches squared. Sorry. So now that we know how to find different rate of changes using different equations, we can use this to find error. Last thing I just want to discuss really quickly is percent error. So percent error is how you know how off or what percent the error is of the entire thing. So in this case, what percent is that 1/2 radius over the normal radius of the manhole cover. So let me write the equation. In this case, because we're doing area, percent error equals dA over the area, which would be using the ideal R, times 100, because you want to get a percent. So the dA, as we just solved for, was plus or minus 8 pi, but because we're doing a percentage, we don't want it to be negative, so just a positive one, over the area. Now if the radius was, ideal radius was 8, then it would be pi r squared, 8 squared times pi, which is 64 pi. Pi's cancel out, you get 8 over 64, which equals 1/8, and then multiply that times 100, and you get 12.5%, and that is your percent error in this problem.